Imagine a neural network, not as a cooperative team, but as a battlefield where every neuron effectively fights for its right to exist. What if sparsity wasn't a choice made by an engineer, but the result of a survival game? This paper explores pruning as a game, equilibrium-driven sparsification of neural networks. Currently, we often treat pruning like gardening. We grow a massive network first, then cut back the branches later based on heuristics like weight magnitude. But this top-down approach essentially imposes sparsity as an external constraint, lacking a theoretical explanation for why sparsity should emerge naturally from the learning process itself. Our media tax exchange. The authors flip the script by modeling network components, such as weights, neurons or filters, as strategic players in a non-cooperative game. In this framework, sparsity isn't forced, it is an emergent property that appears when the cost of a parameter participating outweighs its benefit, making dropping out the most rational move. Let's compare these paradigms side by side. Traditional methods rely on centralized post hoc decisions that remove weights after the heavy lifting is done. This proposal utilizes a decentralized, equilibrium-driven process where parameters compete during training, determining their own fate based on their utility to the prompt. So, how do we actually turn a neural network into a game theory simulation? Let's look at the mechanism. They assign each parameter group a specific participation variable, denoted as $SI. Each group calculates its own utility, defined as its contribution to reducing training loss, minus the costs of staying active, which includes penalties for magnitude and competition with other players. The system reaches a Nash equilibrium when no parameter can improve its situation by changing its strategy alone. If a parameter's utility remains negative, staying active becomes a dominated strategy, forcing its participation variable to 0, and effective pruning it from the network. Does this theoretical game actually result in accurate, efficient networks? Let's examine the evidence. Testing this on simple perceptrons with MNIST, the results confirm the theory. Participation values naturally split into a bimodal distribution, clustering at exactly 0 or 1. The middle ground proves unstable, leading to networks with 98% sparsity, while maintaining competitive accuracy. However, this is just the first move. The current experimentation is limited to smaller architectures like MLPs on MNIST. Generally, scaling this to massive systems like large language models will require solving complex numerical stability challenges related to condition numbers. Why does this matter? It offers a path to end-to-end pruning without complex manual schedules. By providing a theoretical bridge between magnitude-based and gradient-based heuristics, it turns sparsity from a lucky guess into a mathematically explainable outcome. To learn more, head to emergentmind.com.